Hi, everybody. As the music fades out here. Welcome back to Chem 140. So, just some announcements on the bottom of the screen. Last call for quiz number 1 and lab worksheet number 1 is tonight. I know Canvas puts a stamp on the calendar for the day something is due. I don't know if it does anything if the assignment is closing. I don't think it does, so try to get things in by the due date. The 24-hour close deadline after that is just in case you can't make the due date. Because, again, when I didn't have it automatically close a day later and I had it close right when the assignment was done, I just got swamped with, hey, can I get 24 more hours? Something happened or whatever. And I was like, you know what, I'm sick of dealing with this and telling certain people yes and certain people no. Now I just have everybody, I have it open for 24 more hours, and then I just tell everybody no. So I feel a little better about that. What do you want? My cat is here meowing. Do you want to say hi? Maya wants to say hello. Say hello. Maya. Maya, say hi. Maya. Maya. Yeah, there we go. Great. All right. Now that she said hello, I guess I can teach. So. And then I think I answered all the other questions in the chat there. So we're going to finish Unit 3 today. We're going to talk about percent and percent error. So let's just get this out of the way so that we can move on to Unit 4. Talk about density. What is percent? I'm sure that everybody has heard of what percent is. It's just like if there was 60% green, I don't know, then 60 of 100 objects would be green, right? Maybe like 4 out of 5 doctors recommend that you do such and such. That would be 80% because 4 divided by 5 times 100% is 80%. So you've all heard of percentage, so you know the formula. It's right here. What you may not have done with percentage is used it as a conversion factor, because when we use percentage in dimensional analysis, it's actually quite useful. So let's do a very basic percentage question just to show that we know how to do percentage. So in a previous quarter that I taught this class, 37 out of 45 people passed the class. What percentage of students would pass Chem 140 at this rate? And so we would say, okay, well, 37 divided by 45. Now, if I put students in both cases, because we like to throw in our units, right? Well, the units immediately cancel out. And so I get this. 37 divided by 45 times 100. The times 100% is important because that is how you get the percent unit on there with a number that makes sense. So if I just do this right here, 37 divided by 45, I get 0.82. That is a percentage expressed as decimal. When I put the percentage symbol on the end, I have to also multiply by 100. So I get this as my result. Now, in theory, you could say, oh, well, those numbers are counted, and so I should have an infinite number of sig figs, and that would actually be correct. The number 100 right here is an exact number, for what it's worth. If those were measurements, then I would have 2 sig figs, but technically they're not, so I should be writing 82.22222 forever. All right, basic percentage. We know how to do that. Let's do something a little more practical. I have a 5 kilogram steel alloy bar, and steel is 94% iron by mass. What mass of the 5 kilogram steel alloy bar is actually attributed to iron? Now, this is another problem where you're probably like, well, I just take 0.94 and times it by 5, and you just know how to do that. But how do we do that to show that the dimensional analysis makes sense? And I'm going to show you that here so that we can ascertain that, like, yeah, we're allowed to just multiply these two numbers together. All right. So if the steel alloy is 94% iron, then what that is saying is that of a 100 kilogram sample, 94 of those kilograms are iron, right? And I don't have to pick kilograms. I could pick grams or whatever. But I did pick kilograms because that's the units of the bar. And so now what I can do is I can say, well, in a 5 kg steel bar, I can then just use my percentage as a conversion. And then these cancel out, right? And then I have 5 times 94 divided by 100. So if 94% of my bar is steel, and the bar weighs 5 kilograms, that must mean 4.7 of those kilograms are iron at this percentage of iron and steel. And so this is how the units work out. Because normally you would just say, oh, I'm just going to take my fraction or my result as a decimal and times it by the number. And yeah, that's exactly what we did here. But I'm showing you the dimensional analysis to verify that, yeah, we can do this. When in doubt, dimensional analysis it out, right? All right, I'm going to have you try one. More or less the same type of problem. Air is 21% oxygen by volume. If you take a deep breath and you hold it in there, 21% of the air, or 1/5 of the volume of your lungs, roughly, is oxygen. The rest is worthless. It's nitrogen, it's water vapor, it's carbon dioxide. Doesn't help you. In a sample of 1.25 liters of air, how many milliliters are oxygen? Can you write an algebra equation using the part whole times 100%? You can if you want to. The part that we primarily care about is the part whole part. So go ahead and try this calculation. 21% oxygen, 1.25 liters of air. How many milliliters are oxygen? So convert your answer to milliliters when you're done. I'll give you 2 or 3 minutes to do it. We'll go over the answer in a sec. All right, one more minute. We'll go over the answer. All right. So we'll just get rid of that off the screen there. So in our 21% oxygen by volume sample of air, which all air is 21% oxygen by volume, to roughly that number of sig figs. How many milliliters are oxygen? So we could say if I had 100 liters of air, we'll write that just to have 3 sig figs. 21.0 of those liters would be oxygen. And then, well, let's not just stop the calculation there. So instead of printing out the answer and then having to convert that, we'll just do this. Liters oxygen, milliliters oxygen. And in 1 milliliter, there are 10 to the minus 3 liters. That'll save us a step of writing stuff down. So 1.25 times 21 divided by 100 times 10 to the minus 3. I get 262.5 milliliters of oxygen, which I only get to have 3 sig figs, so it becomes 263. And hey, everybody wrote that as right. Very good. All right, any questions, let me know. All right. So I have 2 percentage questions here for you to try. So in 2015, I checked a Scrabble dictionary, and there were 277,663 words that were allowed to be used in the game Scrabble. And of those, 5,846 had 4 letters in them. What percentage of playable words does not contain 4 letters in Scrabble? And then down at the bottom, we have trimix, which is a common scuba diving mixture. 21% oxygen, which is what you need, 35% helium, and the remainder is nitrogen. What is the volume of each gas in a 12-liter scuba tank? Go ahead and try these problems. We'll go over the answers in just a bit. All right, about 1 more minute. We'll go over the answers here. All right. Let's go over here. Oops, that's not what I wanted. All right, so if I go doot, doot, doot. All right, so what percentage of words do not contain 4 letters? So there are 4-letter words divided by total words times 100%. And so that would be 5,846 words divided by 277,663 words times 100%. And this would be the percentage of 4-letter words. If I could type that all in my calculator, times 100. And I get 2.105%, or however many significant figures I should have. These are all counted, so technically I get to keep all the digits. All right. So if I want not 4-letter words, I just have to go 100% minus this number. And so 100 minus the answer that we got was 97.895. And honestly, for that problem, you can have as many significant figures as you want. All right, the next one. There's our mixture for our air in a scuba tank. And so if I have 12 liters of air, well, quote unquote air in a scuba tank, for oxygen, that would be, if it's 21%, so that's 21.0 liters of oxygen per 100 liters of air. And that ends up being 2.52 liters of oxygen. And then for helium, I do the same thing. Except I put 35 in because it's 35% helium. These cancel. And I get that. And then if the rest is nitrogen, I could do 12 liters of nitrogen times whatever percentage is left over divided by 100. Or I could just say 12 liters of air minus the oxygen minus the helium must equal the nitrogen, right? So that would just be 2.52 and 4.20. Now, I'm only going to get to go to the 10th place if I do it this way. But doing that, this is the number that I got. So you could do it that way. You could do it the figure out the percentage way. That way would get you more sig figs. Either one's fine. Total volume has to add up to 12 liters regardless. All right. So the last thing we can do in the percentage section is we can talk about a specific term called percent error. Percent error is a special... So don't they all have sig figs because of the 3 sig figs because of the decimal point? No, we're doing subtraction. So since we're doing subtraction and I'm going to the 10th place, all my answers have to go to the 10th place. Because there is no number in the 100th place here, so I can't subtract those. If we were doing multiplication, then yeah, they'd have 3 sig figs. Right, damn it. Damn sig figs. Sig figs are here to ruin your day for the rest of your life. That's just how sig figs work. Speaking of sig figs ruining our lives, this is where that's going to happen because now we have a subtraction and a division, and this is where everybody screws up on sig figs because you have to do both, right? All right, percent error is a deviation from an expected outcome. If my object that I'm measuring is like 11.2 feet in diameter, we'll say, but the expected diameter is 11.0 feet, I'm off by 0.2 feet. What percentage is that 0.2 feet of the correct thing? That would be my percent error. Because I'm taking whatever percentage the error is. If I have it exactly right, then these two numbers equal each other. When I subtract them, I get 0, and I have 0% error. Okay? The measured value is going to be whatever you acquired as a number. The true value is what we have accepted as being true. So let's do this example together, and I'll show you where the sig figs come into play. Because everyone screws this up. In fact, if you just look at these two numbers, 2.63 and 2.71, how many sig figs should the answer have? And if you're immediately thinking 3, haha, you've activated my trap card. I'm going to get Yu-Gi-Oh on your ass here because that's not correct. So we have to be very careful with sig figs when doing percent error. Don't immediately jump to 3. The correct answer, believe it or not, is 1. And we're going to show how that ends up being in just a second. So percent error is measured minus true divided by true times 100. And it's not 1 because I got 100 here. 100 is exact. So let's enter these numbers. I measured, I being the student, 2.63 was the density that I measured. But the correct density was 2.71 grams per cubic centimeter. And so that goes down here times 100%. All right. What's 2.63 minus 2.71? Well, if I subtract them like this, I'm going to get a negative answer. 11 minus 3 is 8, and then I get 0, 0. So I now have one significant figure in my result for this top part. So now my expression becomes this once I reduce down after that subtraction. 0.08 grams per cubic centimeter over 2.71 grams per cubic centimeter. The units cancel out times 100%. So whatever 0.8 or 0.08 divided by 2.71 is times 100%, and then I have to round it to 1 sig fig. So I got this. And yes, again, there is only 1 sig fig, because this number that we got also had only 1 sig fig. Now, why does it end up being this way? Why is there only one significant figure? And the answer to that question is, as you get closer to the correct answer, your error gets smaller and smaller and smaller, and it becomes harder to identify. If things are harder to identify, they're less precise, right? And so we have a smaller number of sig figs. So when you're doing when you are doing percent error, be very mindful of that situation. So I'm going to give you a few of these to try for yourself. So we can see if you can get to the right number of sig figs, because in theory, the formula is pretty straightforward, right? It's getting the number of sig figs right that's the trick here. So I'm going to give you these problems here. So we have standard sample of oxygen is 2.705 grams. So every student that uses the standard sample should get that result. Any deviation from 2.705 grams is the result of some sort of error. Either the procedure was followed wrong, or they didn't take the correct amount of sample, or whatever. They should get this answer. Here are the answers that these students got. I want you to tell me the correct percent error for each student with the correct number of sig figs. Okay? So report your answers in the chat. We'll go over the answers together in just a bit. One more minute, we'll go over the answer. All right, so let's look at these samples and see if we can calculate the percent error. All right. I see everybody got the same answer for A. So that's always reassuring, right? When everybody gets the same answer. Oh, I have bad news for you guys. There's our formula. And so the measured amount was this, 2.725 grams. The true value was this, 2.705 grams. And if I set those up vertically, guess what happens here? Hold on just a second, actually, because we can do something really funny. Do you see your mistake? Oh, and I can't find the thing that I'm looking for. There it is. Okay. So I'm going to subtract this. And we have, guess how many sig figs there are there? You can't hear that, unfortunately, which is too bad because this is what I played. So yeah, there should be 2 sig figs in that. Because then when I put this back in the result, and you can easily see, yeah, duh, there's 2 sig figs, right? So be careful, that's how I get you. I have so many ways. Times 100. And so I get 0 points. So for A, you should get this. That's why I give you these problems here, where you can make a mistake and who cares, right? Because it's not like it's worth any points. So you don't want to do that on a lab, for example, though. All right, so for B, we got this. And again, we'll set it up vertically. Well, I'm going to end up with a negative number, so I'm going to do it this way. So if you were subtracting a bigger number from a smaller number, I just put the bigger number on top. And then if my minus is floating up here, that just means my answer is going to be negative. I don't know anybody else who does that. I think it might just be me. I sort of come up with these ideas and then use them. So we are doing this over 2.705 grams times 100%. And so the result that I got was negative 0.215. Those grams cancel out. And there you go. Now, notice that there is a negative here. Some variations of the percent error formula use absolute value bars. I personally don't. And the reason for that is because the negative symbol does tell you something. And so this is B. The negative symbol on my percent error tells me, hey, your answer was this percentage off of the correct answer, and the negative means that you were in the direction of it being too small. A positive percent error means that your answer was too large. So negative is not inherently bad. So if you get a negative percent error, it's okay. That just means that you were off in the opposite direction that everyone else was. Well, not everybody else. I'm sorry. Your answer was smaller than the correct answer. Sorry, I was typing things in the calculator when I said that. Okay. So that was B, and then C here is 2.8. Oops, my pen isn't working. Why is my pen not working? What on earth happened? So that's bizarre. So work over here? Yeah, it works over there. I don't know what happened to PowerPoint. Or not PowerPoint, but Photoshop. Does this work? No, the mouse doesn't even work. There we go. Some weird setting in the, like I hit a button or something, I don't know. So for C here, and now I don't have a color for you, so. So there's our formula. I'm going to subtract them vertically. When I do that, I get this. 0.096. So I should have 2 sig figs for my answer here. My units cancel out times 100%. And the answer I get for that one... Oops, I got times by 100. My answer was way too tiny. 3.5% error. There you go. Everybody got that one. Hooray. Alright, that's percent error. Let me know if you have any questions. That's also the end of Unit 3. So, hooray, we did it. I think there is a sound effect after this, so we get to celebrate. Yay. Alright. You're going to get to celebrate by taking a break. So, we'll come back in 10 minutes. We're going to start Unit 4, which is density. Density will be relevant for next week's lab assignment that we're going to do. Oops, hold on. I got to do this to get out of PowerPoint. But I'm going to start the timer. We're going to kick the music back on for Stardew Valley here. And we'll see you in about 10 minutes. Well, look at that. Music fades out just in time. Welcome back. I hope you enjoyed your break. Slides for Units 4 and 5 should be on the screen. There we are. All right. Units 4 and 5 are so short that I put them in the same set of slides. These topics they don't really go with any other topic and are on their own important, but there are not that many things to really talk about. Like, we're going to discuss what density is, and we're going to define it and do some problems with it. But then after that, like, it's now a tool in your toolkit that you can use. I do want to mention that if you look in the chat right now, you can see. So I had a math error, it looks like, on problem B. A student reported that they got negative 0.195. And I want to say that I had like something like negative 0.215 or something like that. And I think I just used the wrong number. I used the answer from A or something instead of the standard number. So in the chat, you should be able to see what the correct answer for B is. And I apologize for that mistake. Thank you for pointing that out. Where is my pen? There it is. Okay. I gotta turn the heater down now because it's getting really hot in here. All right, so let's talk about density. Here's the formula for density. Density is defined as the ratio of the amount of stuff an object has divided by the volume it takes up. So if you have lots of stuff in a really little tiny space, like, say, lead is very dense, you'd get a large number here. Because if this number... Oops. Don't have the pen selected. There we go. If this number is large, but this number is tiny, then you get a large number as a result. But if I have a very large volume and a very small, so if this number is large and this number is small, then I get a small number in turn. So I can manipulate these masses and volumes and get all sorts of different unique results. On the screen are the units that we use for density. Now, these are the standards. You could really use any unit that you wanted to, as long as the top number was some sort of mass. No, not a weight, but a mass. And the bottom number was some sort of volume. Typically speaking, liters or some derivative of liters are preferred, although the standard for solids is grams per cubic centimeter because cubes can be made into very rigid and regular shapes that we can use a ruler to measure with, whereas liquids, you can't do that. So it's important to note that these are the standard units because when we input stuff into the formulas, we're going to want to get things out that have those units. Otherwise, we're just making more work for ourselves. And we'll see that in a little bit here. Now, first, let's show the visual demonstration of density. If I hit escape, does that work? Yeah, there we go. So if I do this, and this should put this somewhere here. Window capture. I want you to capture density column. Let's see here. Oops, that didn't work. There we go. That's too big, though. All right. We'll cover the chat for just a second here. So we're going to sort all of these objects by density, not the glasses. Here are all the objects. These are the liquids that we're going to use, as well as, you can see down here at the bottom, these are some solids that we're going to put in here. So these are the liquids we're going to add. These are the solids that we're going to add. We're also going to add adult supervision and then throw it out because that's stupid. All right, so I'm going to pause right here. We're going to take these liquids and we're going to arrange them on top of each other. Food coloring has been added to the water and the isopropanol, or rubbing alcohol, sorry. Maybe also to the lamp oil. I don't think lamp oil is actually red, but we are going to put all of these liquids in a giant glass casing, I guess, or tube, one at a time. And we're entering them into the in this order in such a way that they won't mix with each other appreciably. And as long as you are careful about this, you will not create layers that mix with each other, and they all separate out. And then you can drop in the objects, and the objects will fall to the correct layer based on their density. And so there we go. So we have sorted some like 17 things here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I lost count. 9, 8, 10, 11, 12, 13. Yeah, 16. There are 16 objects here. And we've sorted them by density. On the right side in red is how far down the object fell, such as this cherry tomato. So you can see it here. The cherry tomato is more dense than water, so it sinks beneath it. And it's less dense than dish soap, so it kind of floats on top of it. I mean, it's trying to anyway. The beads are less dense than water, so they float on top of the water, but they're more dense than vegetable oil, so they're sinking underneath it. And all of these objects are sorted by their density. So that's really cool. Have I heard of sulfur hexafluoride? I have. It makes your voice super, super deep. But it is not less dense than air. It is actually very, very dense, which is why you can like trap it in a bin and float stuff on it, and then it looks like things are just floating mysteriously, and it's actually really cool. We will see sulfur hexafluoride in 161, so I'll mention it there again. But if you want to know more about that and see like people breathing it and then the voice gets like this, YouTube it. Just type in sulfur hexafluoride. It's really cool. Oops. All right, so I'm going to have you try this mathematical example using the formula for density. So very basic application. I'm going to put olive oil and water with these properties and quantities into a tube. They do not form a mixture, so they do separate out. Which one lands on top? Is it the olive oil with mass 18.6 grams and 20 milliliters volume, or the water, which is mass 25 grams and volume 25 milliliters? So, excuse me. Tell me the density of both of them, and then draw a little picture for yourself to indicate which one floats on top. I'll give you about 3 minutes to do it. We'll go over the answers together in just a bit. All right, one more minute. We'll go over the answer. All right, so let's draw a little picture of this. Once we figured out the densities. So, okay, the problem appeared there. Oh, weird. I guess it had the memory. All right, so I've got my density of olive oil is 18.6 grams divided by 20 milliliters. And I need my calculator, which I put my phone on top of. That's not great. I get 0.930 grams per milliliter. So that's the density of the olive oil. If I do this with water, I get a nice round 1.0. The density of water is very close to 1. Okay, which one's smaller? This one is... And so when we draw it in our little container down here, so here's going to be our container. Oops, not if I select that icon, it's not. So, we've got a layer at the bottom. This would be our water. Well, we've got a smaller layer on top because there's less of it. This would be our oil. And they do not mix together. They do not form a homogeneous solution. They remain heterogeneous. Now, why is that? We'll talk about that 161. All right, cool. So that's the conceptual idea behind density. So let's do some more mathematical applications of density, because that's what we're going to be focusing on primarily in this class, is the quantitative and analytical aspect of it. All right, I've given you a version of a density problem that's sort of a unit hell. For instance, you can see that I have a volume in liters, but the density has its volume component in cubic centimeters here. That's not going to work for us, right? We need to make sure that those are the same unit. Now, the first thing that I would advise that you always do whenever doing a density problem is you just write down the formula. And then right there in the problem it says, what must its mass be? So you have to solve for the mass, obviously, and you can plug in the other numbers. But that will only work if you get units that work out, right? So I'm going to let you try and tackle this for about 2 or 3 minutes, and then I'll get started on it too and help you. Tell me what the mass of the glacier is in any units of mass you want, because the problem doesn't specify. I'm going to pick kilograms because that seems appropriate for a glacier. But if you want to do it in grams, that's fine too. All right, 2 or 3 minutes, and I'll see you in a second. All right, one more minute. We'll go over the answer. All right, so let's go over here again. Oops, that's not helpful. All right, so I'm going to rearrange my density equation here. I'm going to solve for the mass, which means I'm just going to multiply both sides by the volume, so that the mass is equal to the density times the volume. So if I input the density and I input the volume, I will get the mass, provided that the volumes all cancel out and go away, right? Well, if this is my density, and then this is my volume, my 7 didn't appear there for some reason. Those obviously don't cancel, right? But what I can do is I can say, well, there are some number of liters in a milliliter, right? So those will cancel. And then what I can do is I can say, remember that fancy conversion I talked about? Where milliliter and centimeter cubed were the same thing? That's convenient. Now I can cancel this one out with this one out, and the only unit that's left is grams. So again, dimensional analysis, your best friend. Just cancel out everything if you can. 0.9167 times 35,720 times 1 divided by 10 to the minus 3. And I get 32744,524, which is really, 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 really big. And it's in grams, so 3.27. How many sig figs do I get? I get 4. Times 10 to the 367 grams. Which is not exactly what I wanted the mass in, but this is a valid answer. I didn't specify what units we wanted. But if I wanted this in kilograms, I think you've seen me do enough metric work for a day. And can be like, yeah, I could just multiply that by 1 over 1,000. That's fine. Excuse me. Just stretching here. So there's the answer, and that is what everybody got. So very good. Sorry, doing production stuff in the background there. There we go. All right. Air has a density of 1.29 grams per liter. What volume of air will have a mass of 32 kilograms? So I'm going to let you try this again. Remember that the units have to match up, so you're going to have to do some tinkering before you start inputting numbers. Solve for your variable from the d equals m over v equation first. We'll write that back up here. Do the algebra first. That's the way you should do it. The algebra is the hard part. Do it first and get it out of the way. All right, a few more minutes, and we'll be right back. All right, just a second more and we'll go over the answer. All right, so the trick to this one is really just making sure that you do the algebra correctly. Because if you accidentally mess up the d equals m over v formula and solving for v, why didn't it erase everything? Oh goodness, why not? Oh, it did this weird thing again. Am I just in a different mode? What is going on? This happened last period. Close. No. Alright, I can write on it again. Okay. Sorry about that. I don't know why that keeps happening. I'm hitting some sort of keyboard button and starting a shortcut that locks me out of being able to draw. Alright, so let's write down the formula. And this time I gotta solve for v, right? Now, you can't solve for something on the bottom. You gotta get it up to the top. So I'm gonna multiply both sides by v. So I get d times v is m. And then I'm going to divide both sides by v. So these canceled out over here. And then now these cancel out over... I'm not going to divide by v. What am I doing? Yeah, let's divide by v. Let's go right back to where we were. Good job, Wes. I divided by the wrong thing. We're going to divide by d. That's what we're going to do. There you go. So that's the appropriate formula for solving for volume. M divided by d. Not the other way around. Now I need to make sure that all of our units are in the same same type of mass. So I've got mass of 32 kilograms. What I'm going to do is I'm going to turn that into grams, just because then it matches up with the density. So there's the mass of my air. And I know the density of the air, so now I can just plug everything into the formula, right? So V equals mass divided by density, which is 3.20 times 10 to the 4 grams, divided by the density, which is 1.29 grams per liter. Now, how do these units cancel out? Let's do a little aside here. If I have A divided by A over B, what is that like doing? When I divide by a fraction, how do I fix... What's the way that we divide fractions? What was the technique that you learned in algebra? What do? You do something with the fraction. What is that? I just can't think of the word. It begins with an R. Multiply by the reciprocal. There you go. Very good. So writing this expression is the same as me writing this expression, right? So if I have a unit on the bottom of a fraction that is also itself on the bottom of a fraction, the other two things just cancel out, right? And then whatever is left down here gets promoted to the top. So Down here, when you see this is the same as me writing grams times liters over grams, and the grams cancel. So the unit that will be left over when I'm done with this is just liters. And so now I can punch that in the calculator. 3.20 times 10 to the 4 divided by 1.29. And it'll be that many liters. 24,806. I get to keep 3 of those sig figs. So I have 24,800. All right, good job. So I have a last little set of density problems for you to try on the next slide here. We'll just put these on the screen here. So go ahead and try these. I'll give you like 6 minutes or so, then we'll do the answers, and then we'll do the temperature lecture real quick. Because temperature is very straightforward, and we're probably not going to use it in this class very much at all. I just want to introduce it to you. So do these 3 problems. We'll go over the answers in just a little bit. 1 or 2 more minutes, we'll go over the answers. All right, answer time. So let's do this. All right, so we got gold. Gold is super dense. I don't know if you've ever had the opportunity to hold something that was made of solid gold. A cheaper alternative would be something like tungsten. Tungsten's even more dense than gold. My dean, my previous dean, I should say, the new dean. I don't know if she has a cube of tungsten in her office because I haven't been in her office yet since the pandemic started. But my old dean had these 2 blocks on his desk, and one was made of aluminum and one was made of tungsten. And you go and pick up the aluminum one, and you're like, oh, this feels really light because it's like this huge cube of aluminum, and aluminum barely weighs anything. And then you pick up the tungsten one, and you're like, holy crap, it's like more than 10 times heavier. And gold is like that. Gold is super dense. So picking up anything made of solid gold is very, very heavy. And look at this. It did it again. I don't know what mode I am putting this into when I just minimize it, but it's totally doing that. Is it me hitting this? No. Is it this? No. Nope, that doesn't do anything. Okay, well, I just have to open the file again. So, boop. Yeah, something I am hitting here is doing this, and it is confusing. Alright. At least it's an easy fix. Okay, so density equals mass over volume. And I want to solve for volume, so we've already done this. So I'm going to spare you the algebra. And we just punch in the numbers as is, really. So mass is 329 grams. Its density is 19.3 grams per cubic centimeter. And so the volume that we would have would be just 17 cubic centimeters, which is not very much, believe it or not. In fact, a way to imagine that, I just picked up my can of seltzer water. A can of seltzer water weighs about 370 or so grams, so just a little more than the sample of gold. So a 17 cubic centimeter or 17 milliliters, so less than 1/10 of 5% of the volume of your soda can would weigh as much as the soda can filled with water. So that's gold. Gold is stupidly dense. All right. What's the density of this beverage? This is, oh, speaking of beverages, so. Okay, well, we know it's mass. We know its volume. So this beverage is very obviously mostly water, because water has a density of about 1. So there you go. Now, the other stuff in there is probably something along the lines of sugar. Sugar adds to the density because you put a lot of sugar into it to make a tasty carbonated drink. All right, and then finally, here's a boat that I want to make. I want to displace this much water. What's the maximum mass that I can put on the boat so that it will still float in water with density 1 gram per milliliter? So this is a little bit about boats and how shipbuilding works. If you have a boat, so here's my boat. It's the side view, so there's the mast, and there'd be like a... There you go, something like that. So there's my sail. And the boat is floating in the water. The water has a density out here. The density of the entire boat has to be less than the density of the water in order for it to float. Now, you might think to yourself, wait a second, I'm putting heavy materials in the water, like metals and stuff. Don't those normally sink? Yeah, they totally do, if they're solid. But if they're not solid and they're full of air, then they'll float because they displace water. So, there is some maximum mass per given volume that I can have for my boat. And that's going to depend on the density of the medium that you're floating in and the volume that your ship displaces. The bigger the ship that you is built to be, the more mass it can carry. Or if you are building in a freshwater lake, which has density water equal to 1 or so, versus the ocean, which has density 1.1, you can put 10% more mass on your boat in the ocean. So the density of my water is going to be 1 gram per milliliter. And the volume of my ship is 65 times 10 to the 6 liters. Well, my units don't cancel out, so I got to include another step to do this. And 1 milliliter is 10 to the minus 3 liters. So what is the maximum mass this boat could have? It'd be 1 times 65 times 10 to the 6 divided by 1 times 10 to the 3. And then what would the units... Oops, I messed that up. Hold on. 10 to the minus 3. And I get this. 6.5 times 10 to the 10 grams. Or 6.5 times 10 to the 7 kilograms. The density of the boat should be equal to 1. Yeah, roughly so. You don't want to go over 1. If you go above a density of 1 for your boat, then you'll sink. Obviously, the purpose of the boat is to remain floating. So you can only put so much stuff on your boat. All right, very good. That's Unit 4, density. Next week, when we talk about the lab worksheet number 2, we're going to talk about density again because we're going to look at some more applications of density. So let's do the temperature lecture real quick. There are 3 different temperature scales that we care about in science. And of these 3, we really only care about 2 of them because one of them is dumb, and that is the Fahrenheit scale. That's why I've isolated it from the others. We have to separate the weak ones in order for the stronger ones to survive, right? No. Fahrenheit is stupid. Fahrenheit is used for confusing Canadians because America is obsessed with a temperature scale that is completely worthless to scientists. And the reason for that is because the numbers that we use for references are not great numbers to commit to memory, and also the number of spaces between those two, also not a great number to commit to memory, right? We like round numbers of 10. This is why we like the metric system. Celsius does that for us. Celsius says, okay, we're going to refer to water just like Fahrenheit does. I'm going to call the freezing point of water, though, 0, and the boiling point of water 100. And that way, we can just have 100 spaces between that. That seems great. Now, this must mean that 180 Fahrenheit and 100 Celsius are the same thing. So 1.8 degrees Fahrenheit is equal to 1 Celsius. And so when we get to the temperature conversion, you're going to see 5 over 9 or 9 over 5, which is 1.8, to convert from Fahrenheit to Celsius. And they're also offset by 32. So Celsius is used in the laboratory because it's more convenient. It's like the metric temperature, right? But there is an issue with Celsius, and that issue is the following. If I were to use Celsius in a formula that required us to input temperature, for example, the ideal gas law, and I put in a temperature in degrees Celsius, you might not think that that's a problem until I try and enter a number like this. If I put 0 degrees Celsius in the formula, well, the formula kind of breaks down. Then everything has to equal 0 here. Even worse, what if I'm doing something like this? Oops, I solved for the wrong variable. I want to solve for R here. There we go. And then I put in 0 Celsius, right? What happens now? Well, you can't divide by 0. You destroy the universe, basically, right? Math falls apart when you divide by 0. You cannot do it. So we cannot use Celsius in calculations. And the reason for that is anytime you divide by it, everything would fall apart, right? So the answer that we have to do is use Kelvin. What the hell is Kelvin, then? Well, Kelvin is just basically Celsius, except that we put the 0 point essentially out of reach. The lowest temperature on the scale here, also known as absolute 0, is set to 0 Kelvin. For Celsius, that's just negative whatever this is at room temperature. So using Kelvin, or in other words, using the absolute temperature scale, allows us to use this for temperatures. So when you get to 161 and you're doing the ideal gas law, you have to put everything in Kelvin. There are some exceptions, and we'll talk about what those are when we do them. But for the most part, we're going to be using Celsius and then converting it to Kelvin. Because we have set up the Kelvin scale to be similar to the Celsius scale, we've set them to have the same gradations. So 1 Celsius and 1 Kelvin are the same thing. So these two are related. It's just that Kelvin is the absolute version of the Celsius scale. Absolute meaning 0 is the starting point, and then it grows from there based on temperature. Celsius doesn't do that. It doesn't start at 0 at the lowest temperature. Now, there is an absolute scale for Fahrenheit. And we need to give it a letter. Can anyone think of a letter to put here? This might be something that you've noticed about temperatures. Like, what letter should go in the blank? I know what everybody is thinking, and That's wrong. No. The correct answer is R. So, just as trivia, this is called the Rankin Scale. And Rankin is also absolute. So down here is 0 degrees Rankin, which is at absolute 0. The Rankin scale is just Fahrenheit, but the absolute version of it. So it's also dumb. We're not going to use Fahrenheit and Rankin because they're silly. But we are going to use Celsius and Kelvin a lot. Here are the formulas for Celsius and Fahrenheit and how to interchange between them. And the most important thing to note here is that these conversion values are exact for Fahrenheit and Celsius. And the reason for that is because we are looking at this 1.8 here and this 32, and that the 32 is just the offset. At 0 degree, or at the freezing point of water, Fahrenheit is 32 higher than than Celsius. And then each Celsius is 1.8 Fahrenheit. So that's where the 1.8 comes in. You may have seen in other formulas this conversion instead, where you see, oh, I'm going to multiply by 9/5, or I'm going to multiply by 5/9. Dividing by 1/8 is the same as dividing by 9/5, which is multiplying by 5/9. So if you see those fractions, I've just sort of simplified it so I have less division bars. So the 1.8 here is correct. Now down here, the conversion for Kelvin to Celsius is approximate because we are measuring Celsius along the Kelvin scale, which starts at 0. And the 0 for Celsius lands on 273.145 whatever. So sig figs will matter for this one. But here, these conversion factors will not affect your sig figs. What will affect your sig figs are the operations that you do. So be mindful that you are doing addition and subtraction with the temperature formulas. In reality, though, what you're probably going to do is go to Google and type in the temperature and say, what is 400 degrees Kelvin in Celsius? And for our purposes, that's good enough. Like, what is 108 Fahrenheit in Kelvin? This slide talks about absolute 0. We're not going to talk about absolute 0 ever in this class. You can think of absolute 0 as just the lowest possible temperature if we define temperature as how much molecules move. If molecules don't move, they're at temperature 0 or absolute 0. And we'll talk about that in 161 and 162 when we get to gas laws and the kinetic molecular theory. I'm not going to make you do these conversions for temperatures. Oops, I tapped ahead too quickly. You can do these on your own. I don't think that this is a worthwhile exercise, especially when there's -1 minutes left of class. So we'll just skip ahead to this. Alright, you probably didn't think that you were going to do units 3 and 4 and 5 today, but yet here we are. So, quiz number 2 will be going up after the lecture video concludes. I am going to put that on Canvas. Quiz number 3 also includes Unit 6, so there will not be a quiz just yet. We're going to do Unit 6 on Monday. It's very short, and then quiz number 3 will appear. So you'll notice that the quizzes are starting to get... They spread out at first, and then they start to get closer and closer together as we complete more and more content. So that is just a feature of the class. Sorry, that is me closing the PowerPoint here. So yeah, as far as assignments are concerned for you at the immediate moment, quiz number 1 and lab worksheet number 1 are due tonight. The assignments do close. You should get an email about 6 p.m. that says, hey, last call. Turn those in before the deadline. That's all I got. Thanks for coming out to the lecture. If you have any questions, hit me up in the Discord, send me an email. I'll be happy to answer them. Have a good weekend and get those assignments in. Take care.